Most people think of radio as wireless broadcast of sound, most often music and speech. But the term radio is actually much broader than that. The broadcast of sound is actually just one application of the extremely useful electrical phenomena that is called radio. As mentioned in the previous course, in order to convey information to somebody, a user must first impose a pattern, which interacts with a medium in a channel, which gets then decoded at the recipient's end, and is finally received in a form in which the recipient can understand it. You see, most of these interactions between the patterns and the medium of the channel are best described by waves. For example, when somebody speaks, they are using pressure waves in order to convey information to somebody else. These pressure waves represent points at which molecules of air are packed closer together and points at which they are further apart. Energy is pumped into the atmosphere to compress molecules together. The high point of the energy which squashes the molecules closer together is called the crest of the wave. The low point of the energy, when the molecules are far apart, is called the trough of the wave. Now, the number of waves passing by in a single second, that would be the frequency, right? Frequency is simply the number of waves passing per second. Just like the ripples on a pond after a stone has been thrown into it, all the little ripples that passed through a certain point would indicate frequency. Radio frequency is identified as number of waves per second or cycles per second. The modern term for this is hertz. The term hertz here does not refer to the car rental company. Instead, it honors the great German physicist Heinrich Hertz, who was the first person to build a device that could create and detect radio waves. Now, radio takes advantage of one of the most interesting of all electrical phenomena, electromagnetic radiation, which is a type of energy that travels in waves at the speed of light. Electromagnetic radiation travels freely through the air and even in the vacuum of space. Radio is simply a specific range of frequency of the electromagnetic waves. The low end of this range is just a few cycles per second, and the upper end is about 300 billion cycles per second, which is also known as gigahertz. That's a pretty big range, but electromagnetic radiation waves with much higher frequencies exist as well and are in fact commonplace. You see, electromagnetic radiation waves with frequencies higher than radio waves go by various names, including infrared, ultraviolet, X-rays, gamma rays, and most importantly, visible light. That's right, what we call light is exactly the same thing as what we call radio, but at higher frequencies. The frequency of visible light is measured in billions of hertz, also called terahertz, and the low end of visible light, which is the red, is around 405 terahertz, and the upper end, which is violet, is around 790 terahertz. Now, as a general rule, and it's very important to remember, is that the lower the frequency, that is, the longer the wavelength, the further a signal can penetrate through solid objects like mountains, walls, etc., or liquids such as seawater. This might explain why visible light cannot penetrate through walls or solid objects, or why submarines use a longer wavelength instead of a shorter one, because the electromagnetic wave has to travel longer distance and has to penetrate through the water and all the obstacles that can be found in the ocean. The same thing applies for FM or AM radio, which we are going to talk about in more detail in just a moment. When you are listening to the radio, I'm talking here about the classical radio, the electromagnetic wave that is sent from a transmitter, which can be far away from you, I don't know, tens or hundreds of kilometers away or miles away, has to reach your radio's antenna. And this is only possible if the wavelength is higher, so that it can penetrate through walls, buildings, and so on. So again, longer wavelengths have lower frequencies and lower energies. Now radio waves, the longer ones, don't have enough energy to interact with the electrons in most materials. And as a result, the waves pass through and around almost everything. So here's an interesting thought to ponder. Radio stations broadcast at a specific frequency. For example, in San Francisco, there's a popular radio station called KNBR, which has been broadcasting on the frequency 680 kHz since 1922. There are plenty of other radio stations in the area, but only KNBR broadcasts at 680 kHz. The term channel is often used to refer to a radio station broadcasting at a particular frequency. For example, if somebody asks me what radio channel I like to listen to when I'm in San Francisco, I would tell him KNBR. Now, an important thing to know is that radio waves travel at the speed of light. And because they travel at the speed of light, we can actually calculate the wavelength of a given frequency by dividing the distance that light travels in a single second by the number of cycles per second. You know, light is pretty fast. It scoots along at 186,282 miles per second. And as a result, the wavelength of an electromagnetic radio wave oscillating at 100 kHz is about 1.86 miles. Alright guys, now let's end this course with a little history. Who really invented radio, you might ask? The history of radio technology is plagued by controversy over the question of who actually invented the thing. The answer most often given is the Italian inventor Guglielmo Marconi. I hope I'm pronouncing it correctly, but many others made important discoveries that give them good claim to the title. Marconi, he was the first person to demonstrate radio successfully and exploit it commercially. In 1901, Marconi sent a message via radio across the Atlantic from England to Canada. Though the message was faint, consisted of nothing but the letter S, and reception of the message wasn't independently confirmed. Nevertheless, Marconi's accomplishment was astonishing, and he made many important contributions to the technology and business of radio. Another great contributor was the infamous Nikola Tesla. In 1943, the US Supreme Court ruled that many of Marconi's important radio patents were invalid because Nikola Tesla had already described these devices covered by Marconi's patents. Tesla was a brilliant engineer who is best known for being the champion of alternating current over direct current for power distribution. He publicly demonstrated wireless communication devices as early as 1893. Tesla believed that wireless technology would be used not only for communication, but for power distribution as well. Was he right? I guess so. If you look at the wireless charger cases, what they do is these chargers transfer energy from the charger to a receiver in the back of the phone via electromagnetic induction. Nikola Tesla already knew that this is going to happen back in the early 90s, which not only demonstrates that he was a genius, but also a visionary like Elon Musk.